have here is basically the dehydration of the aldo product, okay? So again, we talked about this yesterday, where if you don't have conjugated systems, you can stop at the beta hydroxyaldehyde. So such as acetaldehyde stopped here. In order for me to get the dehydration product, I often have to use base. And the thing that I want you guys to recognize to help you out is if I use base and I use a delta sign. So if I normally use a delta sign, which is heat, what I want you guys to recognize, heat always favors elimination reactions. So if I just have hydroxide, and again, I have an aliphatic system that has no conjugation, we will stop at the beta hydroxy system. In order to get it to eliminate, I must then use strong base, but apply heat, okay? On the other hand, with an aromatic system, such as this, notice that if this guy was to eliminate here and lose water, I make a fully conjugated system. So consequently, my point that I was trying to make with you guys yesterday was that this is not isolated, because as soon as it forms, it eliminates a lot very rapidly, because this is a fully conjugated system. Okay. So again, it kind of distinguishes that. Notice that in this slide, it's also using the alpha and beta to emphasize that that's the new bond being formed between the nucleophile as alpha and the beta as an electrophilic center. Again, this was the mechanism for that transformation. So the first step is you make the enolate, because you still have an alpha proton adjacent to a carbonyl that's still acidic. So now you basically have an intermediate that's stable, okay? And then, of course, why is it stable? Because you have resonance. Every once in a while, this guy can eliminate to get to the conjugated species. Okay, so someone asked yesterday, what does E1B stands for? Here it is. It stands for elimination unimolecular conjugate base, okay? So if you like, I could post those notes later on this afternoon. So let's get back to the actual stuff that we should be covering. And again, I apologize for the technical flips. One thing I do want to share with you is that I'm fortunate that I don't have as much material to cover as Dr. Schwann. So one of the things I definitely wanted to share with you today was that I'm really pushing to cover 23 and 24 by the end of this week. In my opinion, the exam for next week will emphasize these two chapters more than the last two chapters, which are mass spec and polymers. What I hope to do is try to finish that material by Tuesday, so that Wednesday could be somewhat of a review session during class. But again, I'm speculating how fast I could. Hopefully, I don't have no more computer. But I have been thinking about how to process this. I want to give you guys ample time to ask questions and stuff like that. So I'm really thinking about trying to push and have Wednesday serve at least an hour of it be a review session, or to address any questions or concerns you guys have for the exam.
Thank you.
Okay. Oops. Okay. Let me get to this one. And okay. So you can also do an aldo condensation intramolecularly. So what we've been talking about is taking two molecules and making one. That's basically called an intermolecular reaction. Inter meaning I-N-T-E-R. But if I have a bifunctional molecule that has specifically an electrophile and nucleophile, and if they react and form a ring system, this is termed an intramolecular reaction. Okay? So we are going to consider intramolecular reactions both in this chapter as well as chapter 24. We're going to be able to make ring systems. And what's really cool about this is one of the things you should have learned in the first semester is that 5 and 6 member rings are very stable. So if there is ever a chance to make a 5 and 6, we're going to do so. Okay. So in this molecule here, I have a ketone and I have an aldehyde. And again, I'm seeing strong base. Okay. Again, I want you guys to realize that hydroxide can it react with a carbonyl as a nucleophile to the electrophilic center? The answer is yes, but you get nada. You get no reaction because gem dihydrates are not stable. So consequently, hydroxide is not going to react as a nucleophile, but instead it's going to function as a base. Are you guys with me on this?
Yes.
Okay, so again, I want to try to train you guys to see how we use these reagents, and that way you just don't memorize stuff, but you actually see how we could apply this. Do I have a base in the reaction? If I have a base in the reaction, then the first thing I want you guys to consider, what is the most acidic proton? Okay, so I have multiple ones. Clearly I have 2 carbonyls, right? So I have an alpha position here, I have an alpha position there, and I also have an aldehyde which has an alpha position. Okay. Now recognize, what is a better electrophile? Aldehydes or ketones?
Aldehydes.
Aldehydes, right? And so one of the things I talked about yesterday was that ketones are very difficult to react with each other because they're not very good electrophiles, because ketones are sterically hindered because you have these 2 long aliphatic groups adjacent to it. Aldehydes, on the other hand, are not sterically as congested, but also recognize, in addition, aldehydes tend to be more electrophilic because alkyl groups are electron donating, whereas aldehydes only have 1 alkyl group donating, whereas this hydrogen's not doing anything. So by far, this is the best electrophile. With that, in my understanding, then I'm going to consider which is the best 2 sites of these to make a nucleophile. Recognize, if I deprotonate this position, count with me. If I make a carbon nucleophile here, I have 1, 2, 3, 4, 5, 6, 7. Are 7 member rings stable?
No.
Okay. In comparison, what if I deprotonate at this position? If I deprotonate at this position, I make a nucleophile. Then let's count. 1, 2, 3, 4, 5. Are 5 member rings stable? Yes. And you can see that this reaction proceeds in 73% yield. And it goes directly to the conjugated system, the alpha beta unsaturated system. Okay. So mechanistically, it's no different. Again, the first step, now that you recognize which proton to extract to give you the 5 member ring. So generally, again, I want you guys to recognize these intramolecular aldo condensations, because they're under thermodynamic conditions. We know that 5 and 6 member rings are the more stable. So if you can make a 5 and 6, go for it. Okay. So if I deprotonate here, okay, that makes the enolate. This is now my nucleophile. My nucleophile is now going to react with the electrophilic carbon of the aldehyde to give me the tetrahedral adduct. The tetrahedral adduct will do an acid-base reaction here to make the alcohol. And then finally, this will do an elimination. Okay. Now let me ask a question. Is there anything wrong in this mechanism?
Can you tell me what page of the slide this is really quick, please?
This is 19.
Ah, perfect. Thanks.
Yeah, the number should be on the bottom right here.
Yeah, I see it too.
Is there anything wrong with this mechanism? So if this question was probably, say, 10 points on an exam, I'm not saying it's going to be 10 points. The way I would grade this I would give the student either an 8 or a 9, just based upon gradient rubrics. Why would the student not get the full 10?
Is it maybe that OH group that's leaving at the bottom?
Okay, what about it?
It's not a good leaving group. It can't just leave like that.
Is it the products? Because we have a water and a hydroxyl.
Yeah. And wouldn't something react again with the ketone?
No. So some of you guys are kind of on it. It has to do with the last step there. Okay? Recall that I talked about the dehydration of the beta hydroxy to the alpha beta unsaturated system. So this species here to that species. That's an E1CB. Right?
Yes.
So in E1CB, what does that mean? It means that I have an intermediate, right? I'm not showing the enolate that's formed. Okay? This mechanism down here is showing it as an E2. Remember, E2 always use 3 arrows. You abstract the alpha proton, and that is a concerted reaction with formation of the double bond and the OH. Okay? I'm lazy. I simply took this slide from a textbook many years ago. But again, I used it because I feel it's a teaching moment. It's an opportunity for me to emphasize why this is wrong. It's not an E2, but it's an E1CB. Okay, which means you should first deprotonate the alpha position and show the structure of the enolate, so you have an intermediate here. And then remember, the enolate then basically comes in and forms this double bond with hydroxide leaving. Okay? One of the things I often see in many textbooks, particularly since page numbers, textbooks don't want to get too large, they often cheat mechanisms to save space. That's my personal opinion of this. That's why they didn't do it the right way, is they're trying to save space. Okay? Sometimes you see proton transfers that magically a proton jumps from one atom to another. Okay? Again, I'll try to showcase that when I draw resonance structure, mechanisms with you. Here's another example. This is an example of an intramolecular reaction to make an important commodity called cis-jasmone, which is the perfume found in jasmine. Okay? So what you're doing in general is any enolate that can form a 5-member ring is going to go to this aldyl product, and because you're going to generate condensation, it goes directly to the alpha beta unsaturated system. Okay, just like what we did previously. Specifically for the synthesis of cis-jasmone, this is what I need. I need to have a cis-alkene over here, but really what I'm using is a diketone here. So what am I doing here? I'm going to abstract this proton at the alpha position, and that alpha position is basically going to attack this carbonyl to make this beta hydroxy ketone. Okay? Now, the subsequent step, notice I'm not showing all the there's no mechanisms here. It's just showing this intermediate. This guy eventually dehydrates to the alpha beta unsaturated ketone. And again, I'm just showing this as an example of how chemists actually use this reaction, the aldyl reaction, particularly in intramolecular, to make some natural products. Here's the case.